In this week's tutorial sequence, we fit a bunch of different logistic regression models, so let's recap really quickly. We started off examining the relationship between visiting the doctor and one binary covariate, which is whether someone is above or below the poverty line. And we found that there was an association between visiting the doctor and being above the poverty line. In the next tutorial, we added gender into that regression model. We know that being female, you are more likely to visit the doctor in the past 12 months. So female was actually a confounder of the relationship between poverty and visiting the doctor. And we found that once we conditioned on gender, we saw a stronger relationship between being above the poverty line and the higher likelihood of visiting the doctor. And then in the final tutorial, we went ahead and added in age into our linear regression model. We found that age really wasn't a confounder of the relationship between poverty and visiting the doctor, but we saw basically how to perform predictions for predicted probabilities of visiting the doctor when you have a continuous covariate. Throughout all of these models, we came to the conclusion that we have evidence in our data that those below the poverty line appear less likely to visit the doctor in the past 12 months. This was a very consistent relationship throughout all of these models. One last thing that we should look at in this case, we looked at this a lot in linear regression, but we didn't really address it that much in the logistic regression, is how do we compare the model fit? We can't come up with the same pretty residual plots that we did in linear regression because we're now dealing with a binary outcome. But we still need some way to assess the model fit. So go ahead and open up Stata and let's look at the model fit of this last model that we fit in the previous tutorial, the 2 binary and 1 continuous covariate. Make sure that you've generated the variable no-pov, which is equal to 1 minus poverty, and you've generated the variable female, which is equal to gender minus 1. And then go ahead and fit the logistic regression model where we have logit doctor, where doctor is our outcome. Then we have 3 covariates, no-pov, female, and age. This is the exact same logistic regression model from the previous tutorial. Now after fitting that model, go Statistics, Binary Outcomes, and then way down at the bottom they have Post Estimation. Click on this first option, say Goodness of Fit after Logistic, Logit, or Probit. Now once you're in this window right here, you're going to see that there's a bunch of different pieces of information that you can display to summarize the fit of your logistic regression model. One good one to look at is this Pearson or Hosmer-Limashow goodness of fit test. I'm not going to go over that in this tutorial for sake of time, but feel free to read about that on your own to learn about goodness of fit in logistic regression models. The summary statistic I'm going to look at is this first one, this report various summary stats including the classification table. So I'm going to focus on this notion of a classification table. So we're going to use this first option. And the positive outcome threshold, change that to 0.8 and hit OK. Now this is sort of neat because what we're doing is we're linking back to week 3 when we learned about sensitivity, specificity, and ROC curves. You can actually use those notions to assess the fit of a logistic regression model. So what you do is you first select a cutoff. And we're going to find essentially the estimated probabilities, p hat. And if p hat is greater than this cutoff, which I'm going to denote C, then you're going to say that someone is classified as a yes or classified as a positive. On the other hand, if pi hat is less than or equal to C, we're going to say they're classified as a negative. So in this case, if they have a predicted probability greater than 0.8, they get classified as a positive. If their predicted value is less than 0.8, they're a negative. And then we come over here and we look at the truth. Remember, we have this outcome, yi, which is equal to 1 or 0. So we know whether they visited the doctor or whether they didn't visit the doctor. So this would be yi equals 1 right here. And over here is if they didn't visit the doctor, yi equals 0. And so we can now look at this table in terms of our cutoff, which is 0.8. So if pi is greater than 0.8, they're classified as a positive. So there were 243 people that were classified as positives and did visit the doctor. So this is good. That means our model predicted those guys well. There were 73 people with cutoff less than 0.8 with yi equals 0. So there were 73 people that had a probability less than 0.8 and who didn't visit the doctor. And then in this diagonal, we have the people who were predicted as positive but didn't visit the doctor, or who were predicted as negative but did visit the doctor. So in this box, we have something that looks like a false positive. In this box, it's something that looks like a false negative. And they actually give us down here sensitivity and specificity. And then they bust out Bayes' theorem, and they actually provide us with a positive predicted value and a negative predicted value for our logistic regression model. And finally, they summarize down here the number who were correctly classified. So I think this is really cool. It brings together the ideas of sensitivity, specificity, positive predictive value, and negative predictive value, and allows you to use those to assess the fit of a logistic regression model. Now, I've only done this for one cutoff, though. Really, the more natural cutoff to use in general is 0.5, but given that so many people visited the doctor in this sample, and the probability of visiting the doctor is really high, using a cutoff of 0.5 isn't that informative. So I chose 0.8 here. But in actuality, you should really assess these summary statistics for more than one cutoff. One way to do this is to plot the ROC curve. To do that, we go binary outcomes, go back down to post estimation, and you click on ROC curve after logistic, logit, probit, IV probit, and hit OK. And essentially what this graph does is that for every cutoff that we have, it calculates 1 minus specificity and 1 minus sensitivity. So this dot represents one cutoff, this dot represents one cutoff, this dot represents one cutoff, etc. So for every different cutoff, it calculates 1 minus specificity and sensitivity, and then it plots those. And it connects them to give you an ROC curve. And so once you have this ROC curve, remember the best ROC curve, perfect discrimination would be if you had something that looked like this. And then this line right here is like the worst model. It's like flipping a coin. You're not really able to predict anything. So anything in between here is, a decent model. You're improving your model, you're improving the information that you have by incorporating covariates. Now, if you wanted to compare a bunch of different models, you could plot several different ROC curves, and you could see, does the ROC curve get steeper as I add in more and more covariates? Or does my model get worse? What exactly is happening with the ROC curve? This is a really cool model diagnostic that you can use. And another piece of information that it gives you the area under the ROC curve. So it gives you how much area do I have underneath this curve? And as your model gets better and better, you can see, as the curve gets steeper and steeper, the area under the ROC curve is going to increase. So this is another summary statistic that you can use to evaluate the fit of your logistic regression model.